Hey, welcome back to Mathematics 0110. This is part 2 of the lesson on asymptotes. Part 1 was about vertical asymptotes. Part 2, this video, is about horizontal asymptotes. When horizontal asymptotes come from taking limits to infinity or limits to minus infinity. So it's something that happens when the function's input value, when the x that you're putting into it gets extremely large or extremely negative. To get a little bit of practice working with infinity, I'm going to go through some examples with numbers that are big, but not that big. So first one, limit as x approaches 500 of x squared plus 2x. What happens there is we get the following. We get 500 squared plus 2 times 500. So 500 times 500. 250,000, 250,000 plus 1,000, so 251,000. It's big. It is a big number. What happens is if x goes to infinity. And we shouldn't write this. We should just kind of skip this middle step, but I'm going to write it anyway because I've always enjoyed plugging in infinity as if it was a number and doing math with it, even though we're not supposed to, and you shouldn't. Infinity squared. So you have a gigantic number times itself. That has to be even bigger. But we don't have a symbol for something larger than infinity, so we're just going to say it's infinity. Plus 2 times infinity. Well, that's just infinity, because we can't write anything bigger than infinity. Now we're adding a big infinity plus another big infinity. Best we can say is infinity. Put a little comment here. We didn't have to do anything fancy for this one. But what if it said, what is the limit as x approaches infinity of x squared minus 2x? How would we do that one? Because when we plug in infinity, we get infinity squared, which is infinity, minus 2 times infinity, which is infinity. We have infinity minus infinity, and it might look like it's 0, and it's not. What we have to do is we have to do the following. Limit x approaches infinity. I'm going to common factor an x out. X times x minus 2. Now we plug in the infinity. We have infinity times infinity minus 2. Well, infinity minus 2 is just infinity. Subtracting 2 from infinity doesn't do anything to it. So we get infinity. We don't get 0. So you do have to be careful with these. It may require you to factor. And if you're going to take Calc 1000, then this is the type of thing that you'll see near the start of the course. You'll see limits involving infinities, and you'll have to do these types of tricks. Let's do the bottom ones now. Limit as x approaches 500, and it's the same function as at the top left, except it's reciprocated. Instead of x squared plus 2x, it's 1 divided by x squared plus 2x. So I'm going to do the same thing we did. I'm just going to plug it in and see what happens. 500 squared plus 2 times 500. And we already simplified that. We already did that calculation. We got 251,000. 1 divided by 251,000. I like to think about numbers like this in terms of a lottery. You know that lotteries have low odds of winning. And you may have heard expressions like, the odds of this happening are 1 in a million. 1 in a billion. And those are small numbers. If you take 1 and divide it by 251,000, you're going to get a tiny decimal number. Just to see how small that is, 1 divided by 251, 1, 2, 3, 0 point, and then 1, 2, 3, 4, 5, 3, 9, 8, 4, dot, dot, dot. So it is a tiny, tiny number. I'm just going to say very small. Equals very small, not big. What's going to happen for the example on the right hand side, if we plug in infinity, we're going to get 1 divided by infinity squared plus 2 times infinity, 1 divided by infinity plus infinity, 1 divided by infinity. Now we think about that in terms of a lottery. So if you have 2 different lotteries you can choose from. One lottery gives you a chance of winning $10 with a 1 in a million odds, and the other lottery also is a prize of $10 with 1 in a billion odds. Which lottery is better to play? The 1 in a million, the 1 in a billion? Well, the 1 in a million is better. Your odds of winning are higher. In both lotteries, the odds are low, but one of them is even lower. The 1 in a billion is lower than 1 in a million. Okay, so what about 1 in infinity odds? How small is that? It's this small. It's 0 small. If you keep making this denominator larger, so 251,000, we'll just add some more zeros, This notation, by the way, 3.98 times 10 to the negative 19, that is, like what is written there is literally what the notation means. 3.984 ... multiplied by 10 raised to the power of negative 19. So 10 raised to the power of negative 2 gives you 1 over 10 to the positive 2, which is 1 over 100. 10 to the negative 19 gives you 1 over 10 to the positive 19, so that means 10 multiplied by itself 19 times. That's in the bottom. So you're getting a tiny, 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 tiny number when you do this. Infinity, it's even worse. Best we can do is we can say it's 0. Now it can get more complicated, and it does. To help us, we need some type of shortcut. So based on the calculations we just did, hopefully what I'm about to say doesn't bother you too much. Then we will accept, without proof, that the limit as x approaches infinity of 1 divided by x raised to any positive power will give you 0. And the limit as x approaches minus infinity of x to the positive r is equal to 0, as long as that power is positive and it can't involve taking an even root of a negative number. So you can't say 1 over the square root of x as x goes to minus infinity is equal to 0, because you can't take the root of a negative number. You just got to be careful about that, and that's where that item where it says subject to domain restrictions, that's what that is referring to. No roots of negative numbers are allowed. You can't zero those away. Based on these 2 statements, so these are statements that we can use without proof. You take a number, a small number like 1 or 10 or 5, and put it on top, and divide by x raised to the power of r, where r could be 5 or 2 or 1. As x goes to infinity, you're going to get something small on top, something finite, and something huge in the bottom. So you're getting that 1 over infinity type of a situation, which is going to output 0. Statements we can use without proof. So let's look at the first example here. This is just equal to 0 using above this statement with r equals 3. Just to let you know, you don't have to say that. You don't need to say anything. You don't need to write that to get full marks. You can just say equals 0. One underneath is also 0 using r equals 2/3. this doesn't look very powerful. It seems like a lot of fuss about something that isn't profound. 1 divided by x to the power of r is equal to 0, and here we have similar. Oh, I should make a comment about the 7. So the above says 1. What changes if there's a 7? Well, it's just 7 times whatever we were supposed to get if there was a 1. So if there was a 1, we'd get 0. Now there's a 7, so we're going to have 7 times 0, which is 0. So really, if we wanted to, we could rewrite the above statement that we could use without proof and say little a, or capital A, or c over x to the r as x goes to infinity or minus infinity. That's also going to go to 0 for any constant c or any constant a, or whatever letter you want to call it. So additional constants on top or additional constants on the bottom won't result in either of these statements being violated. It doesn't matter if it's a 1 or a 7 or a 3 on top. All right, now here's where we use that type of a theorem in a more involved problem. We have a rational function, 12x to the 4 minus some stuff and plus some stuff divided by 3x to the 4 plus some stuff. And the question is, what happens to this function as x goes to minus infinity? Now keep in mind, we're talking about what is going to result in a y value. Limits are like function evaluations. When you plug a number into a function, so when you say like, what is f of 5? What you're doing is you're getting a y value out. Think about how you make a table of values. Limits are the same. You're plugging an x value into a function in a different way using a limit, and what's going to come out is a y value, the height of the function at that point. I'm going to cheat for this one. I'm going to do it the proper way, but before I do it the proper way, I want to show you what the answer is. So 12x to the power, I got the brackets, I think. 12x to the power 4 minus 6x to the power of 2 plus 9. And then divide by 3x power 4 plus 2x. So what we're looking at is what happens to this function. There's all this weird stuff that happens. Like, look at all these weird features. There's problems at x is equal to 0. There's a problem at, let's see, common factor x out. I get x times 3x to the 3 plus 2, so I get a weird cube root problem somewhere else. So this function has pathological behaviors around this region, in the middle there, near 0. But the question isn't asking about that. It's what's happening as x goes to minus infinity. So what's happening out this way? And look at what's happening. The function is leveling off. It's getting closer and closer and closer to a y value of 4. If you follow it across, it's approaching 4. So that's what we want to get out of the calculation we're about to do. We want to get 4 out of that. That's what the graph is telling us. And here's how we're going to get that 4 without having to make a picture. If you try to plug in minus infinity right away, what happens? You get stuff involving infinities on top, stuff involving infinities on the bottom. I'll call that infinity over infinity. We cannot say that is 1. For the same reason we can't say 0 over 0 is equal to 1. This is an indeterminate form. Similar problem to 0 over 0. We have to do something to this. Now, factoring this is not going to help us. But doing something else will help us. What I'm going to do is I'm going to use the most powerful trick in all of mathematics for solving problems. And we've done this already. Not this same trick, but a related trick. I'm going to divide by 1. But I have to use this particular form of 1. As x approaches minus infinity of 12x to the 4 minus 6x squared plus 9 divided by 12x to the 4, no, what am I doing? 3x to the 4 plus 2x. I'm going to divide by x to the 4 over x to the power 4. That's equal to 1. Same thing on top and bottom. Now, why 4? 4 is highest power of x. You look for the highest power of x inside the expression. It has to be in fully expanded form. It can't be in factored form. If it's factored, you got to FOIL it all out. You got to expand it all out. Now, after you do that, you look for the highest power of x that appears, and then you divide by x to that power, divide by x to that power. So in this case, x to the 4 divided by x to the 4. Yes, you can change that into multiplication by the reciprocal, which is multiplying by x to the 4 over x to the 4, but don't do that. Instead, I'm going to take everything on top and divide it by x to the power 4, and take everything on the bottom and divide it by x to the power 4, because that's what this is telling me to do. As x approaches minus infinity, I have 12x to the 4 over x to the 4 minus 6x squared over x to the 4 plus 9 over x to the 4, all divided by 3x to the 4 over x to the 4 plus 2x over x to the 4. Okay, next step is I'm going to use the laws of exponents to simplify these. X to the 4 over x to the 4 cancels. X squared divided by x to the 4 gives me 1 over x to the power of 2. 2x over x to the power of 4 gives me 2 divided by x to the power of 3. So I'm going to do all those cancellations. (12 minus 6 divided by x squared plus 9 divided by x to the power of 4 divided by 3 plus 2 over x cubed. And now we can apply that limit to all 5 of those pieces separately. Limit of a constant is just a constant, so it doesn't do anything to the 12. The second piece, this is with r is equal to 2, it goes to 0. Since r is equal to 2. The 9 over x to the 4, that goes to 0. I'll get rid of the since. It's kind of confusing things. So the third piece is with r is equal to 4. So 1 over x to the r with r greater than 0. We're going to get that component going to 0 when x goes to plus and or minus infinity. The 3 stays as it is. And the last piece goes to 0. So we get 12 minus 0 plus 0 over 3 plus 0. We get 12 over 3, which is 4, as needed. Now let's do the next one. We get infinity stuff divided by infinity stuff. It's an indeterminate form. We can't say it's equal to 1. We can't say it's equal to infinity. We can't do anything like that. So what we'll do is we'll do the same trick. We're going to divide by 1, which in this case is dividing by x to the power 4. Again, it's the same division. Highest power of x that appears anywhere. So I'm going to divide by x to the 4 over x to the 4. Choosing 4 as the power on x because it's the largest power that appears inside the question. Now I'm going to take each of those pieces and divide them by x to the power of 4. So the first piece, 12x cubed divided by x to the power of 4, is just 12 over x. Second piece, 6x squared divided by x to the power of 4 is 6 over x to the 2. Last piece is just 9 over x to the 4. Nothing happens. And then the bottom, we have 3 plus 2 over x to the power of 3. Okay. Now we use the theorem. I'll put the theorem down here. Okay. Theorem says that the limit as x approaches plus or minus infinity of 1 over x to the power of r equals 0 for r greater than 0. So I can use that rule for the 12 over x, that goes to 0. The 6 over x squared goes to 0. 9 over x to the 4 goes to 0. 2 over x to the 3 goes to 0. And then I'll write that all out. We can drop the limit since we just got rid of all the x stuff. So we have 0 minus 0 plus 0 over 3 plus 0. That's 0 divided by 3. So 0 pizzas shared among 3 best friends. Each person gets 0 pizza. 0 divided by 3, 0. And that's the value of the limit. Now what does that one look like? So I'm going to go back to Desmos. All that changed was this power 4 on top is now power 3. And this is the graph. And this time the y value, when x goes to minus infinity, it's leveling off at very, very slowly. It's supposed to be leveling off at 0. Make sure I input everything correctly. Yes, okay. It's just very slow. Okay, another example. So this is infinity over infinity. I'm going to divide by x to the 5 over x to the power of 5. Notice that each time I'm writing fewer steps. If you want, you can write all of them, like the example left-hand side here, and show all the steps. Or you can abbreviate the steps, like when I'm showing in the right-hand panel, is cutting out some more of the steps. Or what I'm doing here is directly on the question, I'm saying divide everything on top of x to the 5, divide everything on the bottom of x to the power of 5, and we get the following. We do that. Limit x approaches infinity. So the first term, 3x to the 5 over x to the 5 is just 3. Bottom term, 2x squared over x to the 5 is 2 over x to the 3. And the last term, 5 over x to the power of positive 5. Then in the denominator, I have 6x to the 4 divided by x to the power of 5. So that'll be 6 over x. And the last one, 4 over x to the power of 5. Next, we can use the theorem. That the limit as x approaches plus or minus infinity of f of x. Oh, 1 over x to the r, what am I doing? 1 over x to the r equals 0 for r greater than 0. So looking at the pieces we have, which pieces look like this? Constant over x to the power of r. 2 over x cubed, that goes to 0. 5 over x to the 5 goes to 0. 6 over x goes to 0. 4 over x to the 5 goes to 0. Now I'll write down all the pieces. We get 3 minus 0 plus 0 over 0 plus 0. We get 3 over 0. Which is undefined. So let's see what that looks like in Desmos. So that's 3x to the 5 minus 2x squared plus 5, and then 6x to the 4 plus 5. There we go. Okay. So this is a weird looking graph. So it looks like. And notice what happens when x goes to positive infinity. The y value doesn't settle down at all. The y value keeps going up, 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 up forever. It never settles down. So there is no number that the function comes to rest at as x gets larger and larger and larger. It grows without any bound. Okay, next example. Notice in all of these, I'm not making any distinction between plus infinity and minus infinity. I'm treating them the same way. And it really only matters if you have roots, if you have radicals. Anyway, so what's the highest power of x that appears here? The highest power that appears here is x to the power of 2. So I'm going to divide everything on top by x squared, and I'm going to divide everything on the bottom by x squared. Also, it's worth noting this is an infinity over infinity situation. Okay, so limit x approaches minus infinity of 12x over x squared, so 12 over x minus 8 over x squared, all divided by 3x squared over x squared, which is 3, plus 8x over x squared, which is 8 over x. Now we apply the theorem at the bottom. Both pieces on top get turned into 0. The last piece on the bottom gets turned into 0. What do we have left? We have 0 minus 0 over 3 plus 0. We have 0 over 3, which is 0. And what does it look like? If we go to the graph, let's see. (12x minus 8 over 3x squared). 3x squared plus, squared plus 8x. So it has all types of weird behavior in the interior, but I'm interested in what's happening when x goes towards minus infinity. So I'm going to look at what the graph does in that direction, and the graph is getting closer and closer and closer to 0, further out towards minus infinity that we go. Okay. Let's do the same thing. I'm going to divide everything on the first one. I'm going to divide everything top and bottom by x to the power 4. Since we have an infinity over infinity type of situation. So that's going to be limit as x approaches infinity. 3x to the 4 over x to the 4 is 3, plus 5 over x to the 4, divided by 6x squared over x to the 4 is 6 divided by x squared, plus 4 divided by x to the 4. Then use the theorem. And what do we get? We get 3 plus 0 over 0 plus 0. We get 3 over 0, which is undefined, dne. And what's happening here is the function is growing larger and larger. Okay, last one. For standard examples, and we'll do some tougher ones. Okay, I kind of always get ahead of myself, start dividing by things, but first we should examine it. We have infinity stuff upstairs, infinity stuff downstairs, so this is an infinity over infinity situation. I'm going to divide top and bottom by x to the power 5. And actually I have to do another aside. A question this is another reason I really don't like doing this online teaching stuff. I want to see you in class and have you ask questions. When you see this material the first time, a common question that's asked in class, hand will go up and someone will say, how come you didn't show us this before? How come we didn't just divide all the other examples by x to the power divided by x to the power? How come we were factoring and doing other stuff? But if you look at those, the theorem that we're using did not apply. This theorem is only for limits to infinity. We were not doing limits to infinity. So be careful. If we're not doing an infinite limit, don't divide by x to the 5 over x to the 5. Like, don't divide by x to a power over x to a power. It will not help you. It will make it worse. It will make it harder to solve the problem. So this technique is specific to infinite limits involving rational functions. It's not something that you can extend to limit as x approaches 0, or limit as x approaches 3, or limit as x approaches -10. It's only for limits to plus infinity or minus infinity. Okay, so let's keep going with this one. We're going to divide everything on top by x to the 5, everything on the bottom by x to the power 5. So limit x approaches infinity. 12x to the 5 over x to the 5 is 12 over 8x to the 5 divided by x to the 4 over x to the 5 is 1 over x, so we have 3 over x, plus 8x cubed over x to the 5 is 8 over x squared. And now we apply the theorem to each of those pieces. Limit to infinity of 8 over x to the 5, that goes to 0. That's an r of 5. 3 over x, that goes to 0. That's an r of 1. And 8 over x squared, that's an r of 2, so it goes to 0. Limit of a constant is just a constant, so the 12 stays exactly as a 12. And 12 minus 0 over 0 plus 0. 12 over 0, which is undefined, dne. Now, before going to the next slide, I want to look at all these examples, see if we can see a pattern. So look at these two. On top, on the left-hand side, the term that had the highest power of x was x to the power 4, and the bottom, x to the power of 2. So the top is more powerful than the bottom. If the numerator and denominator were in a race, like on a road, and it was, you know, the person with the checkered flag waves the flag and go, and they went off racing forward, the top's going to win. The power on x is larger. I'm going to show you with a graph. I'm going to graph the top and bottom separately. Like, you're dividing one by the other one, but I can graph them separately just to show you, which one's stronger, which one's faster, whatever term you want to use. Okay, they're both pretty strong. I'm going to choose my x-axis a little bit better than this. I'm going to go from -2 up to 10. Okay. I'm going to zoom out a little bit and look at what's happening. When x is 4, the green curve corresponds to 6x squared plus 4, has this y value. So when x is 4, the y value is 100. And then the blue curve, when x is 4, I gotta keep going. Okay. So the blue curve, when x is 4, the y value is 773. So blue curve is growing much more quickly than the green curve. So 3x to the power 4 is growing much more quickly than 6x squared plus 4. So what's happening is you're getting a much larger number on top than the number on the bottom. You're getting something that's essentially growing to infinity. Same thing's happening on the right-hand side. I won't graph that one, but notice that x to the power 5 is a stronger term on top than the strongest term on the bottom, x to the power 4. So it's the top, and this one's also going to grow more quickly. You're going to get a bigger number on top than the bottom. As x goes to infinity, you're going to get dne. Does not exist. Okay, now let's look at the previous examples. The left example here, we had x to the power 5 on the top as the highest power, x to the power 4 on the bottom as the highest power, and we got undefined, which I should also write dne. So if the top is stronger than the bottom for a rational function in fully expanded form, then the limit will not exist. You'll get a function that just grows and grows and grows. It's not a vertical asymptote. I should point that out. A vertical asymptote is defined as limit as x approaches a, where a is a number, not infinity or minus infinity. Okay, now look at the right-hand example. Our answer was 0, which is perfectly defined, and the top, the highest power of x on top is x to the power 1, highest power of x on the bottom is x to the power of 2. So the bottom is stronger, and the answer is 0. Look at the next one. On the right-hand side, highest power is 3 on the top, highest power is 4 on the bottom, and the answer is 0. So the bottom being stronger, the bottom having a higher power of x means that the value of the limit when x goes to infinity or minus infinity, the value of that limit will be 0. One to the left of that. X to the 4 on top, x to the 4 on the bottom. It's like a tie, kind of. It's a match. They're equally powerful. So what happens when x goes to infinity is everything's going to get canceled out except the number in front of x to the highest power on top divided by the number in front of x to the highest power on the bottom. So 12 divided by 3. Everything else disappears. We get our 4. So those insights are captured here. That if you have a polynomial on top divided by a polynomial on the bottom, it has to be in fully expanded form for both. Both must be fully expanded to use this trick. Then if the bottom has a higher power on the polynomial than the top, then the value of the limit will be 0. If it's reversed, if the top has a higher power than the bottom, then the answer will be dne. And if they're equally matched, if they both have the same highest power, then it's the last term. We'll have the leading coefficient of the strongest power on top divided by the leading coefficient of the strongest power on the bottom. So this is if highest powers match. Highest powers are the same. On top versus bottom. And I gotta add to this, or x approaches minus infinity, or x approaches minus infinity, or x approaches minus infinity. It's for plus and or minus infinity, all these shortcuts. And the reason for it is this, all this stuff that we just did. Dividing by x to the power by x to the same power, it will always work out this way. And you can prove it if you want. Okay. So inside each of these, I'm going to use that shortcut. So first one. This is an infinity over infinity situation. The long way is to divide by x to the 4 on top and x to the 4 on the bottom. Use the theorem, but our shortcut says they both have power 4. Coefficient with power 4 divided by coefficient with power 4. So coefficient just means the constant that's in front of x to that power. So we're going to get 36 over 12, which is 3. That's our answer. Okay, next one. We have infinity over infinity, so we're going to have to do something. We could divide top and bottom by x to the power of 12 and use the theorem, or we can use a shortcut and just say it's equal to 0 since the bottom is stronger. Since the bottom has a stronger power. Okay, next one. 3x to the 8, that's the strongest term on top. 6x to the 3, that's the strongest term on the bottom. We're going to get dne, since the top has a stronger power. Bottom row, you can't just launch into it. Remember, it has to be in fully expanded form. If you look at it in the way it is, it may appear to you that the top has the highest power of x to the 3, the bottom has the highest power of x to the power 4, so the answer would be 0, but it's not the case. If you expand it out, you get the following. Limit as x approaches infinity of 10x to the 4, so just expanding that expression, 10x to the 4 plus 35 x to the 2 divided by 2x to the 4 plus 9x plus 1. Now the powers are matched. We have a power 4 on top, power 4 on the bottom, so our answer will be the ratio of the coefficients, of the leading coefficients. 10 over 2, which is 5. So matching, since matching highest powers on top and bottom. Okay, next one over on the right, we should expand it out as well. It looks like the highest power is 1, but it's not. The highest power on top is 2. After we expand, we'll see. So limit as x approaches infinity, we have to FOIL. 3x times 4x is 12x squared plus 3x times negative 1 plus 2 times 4x, so 8x minus 3x, we get 5x minus 2 all over 6x squared plus 4. Now the highest power on top is power 2, highest power on the bottom is power 2. It's going to be the ratio of the leading coefficients. So 12 over 6, which is 2. So it's the same reasoning as on the left-hand side. A warning that I don't know if I did that here. I should have. A warning I want to give you is you can't always trust that the first number is the highest power. You got to look across the entire thing. Polynomials are not always written in order. So if you look at the middle example, top middle, limit as x approaches infinity of 3x to the 4 plus 5 over 6x to the 12 plus 4. If the bottom instead was written as, let's say, 2x squared plus 6x to the power of 12. The answer would still be 0 because the highest power on the bottom, the 6x to the power of 12, that power is higher than the x to the power 4 on top. So again, the order of addition of the terms doesn't matter. It's just look at all of them and pick off the highest one. Okay, last example. We have a power 7 in the denominator, and after we FOIL, we're going to have a power 2 in the numerator, so our answer is going to be 0, but I'm going to fully do the FOIL anyway, just to reinforce the habit that when you want to use one of these shortcuts, or even if you want to divide by x to a power over x to a power, when you want to use either of those methods, you need to fully expand the expression. So limit x approaches infinity, 3x times 4x is 12x squared, and then I have 3. Oh, it's going to be the same. Oh, it's exactly the same. Okay, plus 5x minus 2 over 6x to the 7 plus 4x. And we're going to get 0 since the bottom is stronger. Okay, and let's see what's left. Probably make a third video. This one's getting kind of long. Yeah, I'll make a third video for the last bits. Okay, so we'll do some more examples and look at graphs and look at examples involving exponential functions in this third and last video for this section.